Welcome to this video on the lens equation. In this video we're going to be taking a look at some of the patterns that create images when we're dealing with lenses. I'm using this really cool simulator from GeoGebra. The authors here are listed and it is really fascinating and a really cool simulation. I have a description in the link below, so thank you to them. Now what I'm going to be doing here is collecting some data and then taking a look at how I might graph that to create an equation that can predict where an image is going to form and how big that image is going to be. So let's just get our bearings here. We have an object, here it's an arrow, and we can move this object around and we can move it closer to the lens, or we could move it further away from the lens. The image forms over here where light rays that have refracted through the lens intercept. So let's take a look at this. Now, if you haven't watched the video on what creates an image, you want to check that out because it will help give a lot more background to this explanation. So let's say light is coming from the sun. Let's say the sun's up here. Well, the sunlight hits this object and reflects off of the object. So that's these rays over here. Now they've only picked 3 specific rays to show the formation of the image. But there would be, of course, maybe an infinite number of rays bouncing off from the sun, bouncing off the object. Now the rays come off of the object, they hit the lens, they refract when they hit the lens, or they bend, and the position where those rays actually intersect is what we define as an image. So for the first set of images that I've created here, you see I was moving, if you look at the data table, I was moving the object closer and closer to the lens. Now I'm making it less than 3 centimeters tall, which is what I had originally placed over here, just so that it's easier to see, because when it's a little bit taller, the lines go off the page. So I went from 10 to 9 to 8 and so on. As I got closer, we can see the image is actually getting larger as we get closer. And for some of you may notice that they're all negative values. And that's going to be something that we're going to look at, is that there's a pattern associated with the fact that these are negative values. Now these are all defined as real images. Those are images where the location of the refracted rays, that's where they actually do intersect. So I could place a screen at this location and we could actually see the image projected onto that. So everybody in the room would be able to see that image projected. Now, we get to the point of the focal point, which we discussed in that previous video, and this is a converging lens, so it causes light to converge. It's also known as a convex lens because it flexes out on either side. What makes one lens unique from another is the focal length of that particular lens. So if I were to use the lens to focus light all the way from the sun or from any pretty far away light source, all those rays would converge on the focal point on either side here of the lens, depending on where the light source was. That's one way to find the focal length of a lens. So if I change the focal length, you see the actual physical structure or geometry of the lens changes. We get a fatter lens when the focal length is very short, and when the focal length gets longer, we see a much thinner lens. But all of these lenses are considered to be small or thin lenses. What we see here happening though is as we get closer to the focal point, the image gets larger, so the magnitude of this value is getting larger, but the values are all negative, which means that the image is inverted. This is something that we see happen with real images. Real images are always inverted from what the object is. Now when we say inverted, it's not necessarily upside down, it's just in the opposite orientation to what the object was. So if I started the object being upside down, the image would be right side up according to our view, but we would still say that it's inverted from what the object was. So we can always switch those things around just to show. Now, another convention is that even though my object is placed on negative values on this side, we always make the object distance a positive distance, and we're going to talk about why that is in a minute here. Now, all of a sudden, when we hit the focus point, there's no intersection of these rays. And so what we say is that no image is formed. This is a very unique position for the object to be in because it allows us to do some analysis on what it means not to have a real image. As we jump the object into the focal length, you may notice here that the image has shifted from being over here on the opposite side of the lens to being on the same side of the lens, and now these lines, which are never intersecting because they're diverging, our eye can actually trace those lines back to a point where they would have had to have converged or come from in order to diverge in the paths that they're taking. These are what we refer to as virtual images. And you can see here that as I get closer again to the lens, the opposite happens. Instead of the object getting larger as I get closer, now it starts to get smaller. But the values have switched to being positive because this has flipped right side up, which is a very interesting determination. For looking at the image distance here in these cases, we see that the image distance was always a positive value when I was dealing with a real image. But when I'm now dealing with a virtual image, all the values have become negative, and we're going to discuss that again in a few minutes. So we see here that the object is inside the focal length, and because of that, there's no way for these light rays to actually intersect. So our eye would have to be looking into the lens from this side, from the right-hand side, into the lens to actually see this image of the object. And this image would be a larger image, as we can see here, than the object height, but the image would be a virtual image. Now, the reason we refer to this as a virtual image is because it's not there until somebody actually looks into the lens to actually see it. It cannot be projected. Another thing that's interesting is that virtual images always form upright. Now, when we say upright, again, we're talking about in the same orientation to the object. If I flip this down, we would still consider that upright in terms of the object. Okay, so it's always relative to the object. Virtual images can only be seen through an optic, in this case, this convex lens. So you have to be looking into the lens in order to see it, whereas real images can be projected. So interesting things happen. Now, like I said before, the focal point is an interesting point because it forms neither a virtual nor a real image. Now I'm trying to get it to go exactly on the focal point, and there you can see they're parallel rays. They'll never intersect in real space, but they will also never intersect in the virtual space because they are parallel lines based on the geometry of where I place them. Now, what's interesting here is that we can then look at this sign convention. The image distance for real images is always positive, and the positive space, if you look here, is where the object is always placed. So we would say that these things occur in real space. There's an actual position that you can put a screen at that will show an image. Virtual images have a negative value in the front because we can't ever actually put a screen in this place. So the negative sign symbolizes that these objects or these images cannot be viewed except by looking into the optic or the lens. They would appear as if they're this far away from the lens, but they aren't actually intercepting at those places. Now I'm going to do something here, switch to Desmos, and I have input my values. Now I input them in two separate sets. The first set over here are these object distances. The second set over here are these object image distances for the virtual image. So we have the real values and the virtual values. Now if we look over here, we see that we get this kind of inverse shape over here for these values. So as the object gets closer to the lens, so as this value, the object distance, gets smaller, the image distance, okay, is getting greater. So if I'm looking at it in this direction. The opposite happens for the, let me just shift this up here, the opposite happens for the virtual images. But what's very interesting is that I see that this set of values is approaching a vertical asymptote and a horizontal asymptote where both values are 4. And the same thing happens over here. So if you've taken a math class where you've studied conic sections, you know that these are actually, this graph is a hyperbola. It's kind of on both sides where of a vertical and a horizontal asymptote. And for the eagle-eyed among you may notice that these values being 4, that is actually the focal length of the lens. So if I just did the focal length of the lens, the asymptotes would adjust. Now mathematically we know that a function is not defined on the asymptote. There's no output value for an input on the asymptote. And that's the same thing here. I can have an input value of 4, the object distance, but I'll have no response, no value, image value for the image because it is on the focal point and the rays will never intersect. So it's kind of cool how the math term for an asymptote, where the value doesn't exist on that line, we would have the same idea in this case over here. Now what we can do is we can linearize this data and take a look at something that will eventually get us here to the actual lens equation. So let's go ahead and do that. So what I did to linearize this graph was I actually took the inverse of both the x values and the y values. So originally I had 10, 9, 8, and so on, 6.67 and so on. And what I did was take the inverse of all of those and graph those. And we see they fall all along this line here that actually has a slope of -1. Now what's so cool about this is we look at this intercept value here and we see 0.25, and this intercept value here is also 0.25. Of course this is an x-intercept and that's a y-intercept, but they're the same value. And if you're thinking about the asymptotes here, you might be seeing that this is actually 1/4, where the asymptote vertically and horizontally were both 4. Now the intercepts are both 1/4 with the slope of the line being -1. So if I go ahead now and try to come up with an equation that would make up this lens equation, we know this is in the form of y equals negative mx plus b, this graph. But I'm going to change the y and the x to be representative of what we actually graphed. Now the y value on these was the image distance, but remember it's the inverse of that, so it's 1/, the image distance is equal to, the slope is -1, so I'm just going to leave that as negative. The x was the object distance, or the inverse of that, so 1/, distance object. And what we see now is that the intercepts are both 1/, or this one particularly here for this function is 1/, the focal length, which is really cool. So now if I rearrange this slightly just so I can get rid of this negative sign, what I see is 1/, the image distance plus 1/, the object distance equals 1/, the focal length. And this is known as the lens equation. Now it can also be used for mirrors, and what you can do is, if you know the focal length of the lens and you know the object distance, you can calculate the image distance based on the other values, and you could calculate all these values. Now whether you got a negative or a positive value would determine whether that was a virtual or real image, and you can always compare these two values knowing if your object distance was within the focal length or not. So this is a very useful equation that can let us make those sorts of calculations. We can also collect data and figure out the focal length of a lens based on the object image distances that we have. I think it's also just a very cool linearization that the two asymptotes are the same as are the two intercepts when we do the linearization. So I hope that helped make a little bit more sense of the lens equation, and we'll take a look at some other things in the following video.